for the do now, there are two questions here. So one is focusing on indicators, and I'm going to talk about kind of the most important thing about an indicator. And then number two is actually looking at particle diagrams for each part on the titration curve. And so it says you should have 5 particle diagrams, but I'll actually do it over here, like while we're doing it, so you can just draw what's in here as we look at the titration curve. For number 1, you want an acid-base indicator that shows the equivalence point of pH 5. How do you determine which indicator to use? So if you want the indicator to change color at a pH of 5, you want to look for the indicator that has a pH range in which 5 falls. Just like buffers, the pH range of an indicator is the pKa plus or minus 1. So we determine which indicator we want to use in this titration by looking at the pKa. The range is pKa plus or minus 1. We'll look at an example today that's looking at indicators. But if you look at the pKa and you add 1, you also subtract 1, that gives you the range. So how can you determine which to use? We'll just say pKa plus or minus 1, and we'll kind of go from there. That's the only thing you need to know about an indicator. An indicator is a weak acid, and when the indicator hits a certain pH, right, it's like a buffer, a weak acid and its conjugate base. Within the pH range, so pKa plus or minus 1, it changes colors. So phenolphthalein that we looked at before turns pink in a pH range of 8 to 10. Its pKa is about 9. So we determine which indicator we want to use by looking at the range, pKa plus or minus 1. Because they all change, they're all different. It's almost like a catalyst where it's in the container, but it's not affecting the reaction itself. So you don't have to worry about the indicator interfering with the reaction. And then number 2, draw a particle diagram to show what is present at each point during this titration. So we have this titration curve here. What we want to do first is we want to figure out what kind of titration this is. So where we start. So notice it says volume of 0.1 molar NaOH added. So that means that up here in the burette is NaOH. I'll move all of these off to the side. So we have NaOH up in the burette. I'm going to use A- just to help with particle diagrams, make it a little bit easier. So let's just over here off to the side. In the beaker, I actually have to figure out, is this a strong acid or a weak acid? You can look at the equivalence point to figure out if it's a strong acid or a weak acid. We know that it's NaOH in the burette because that's what the x-axis says. That's a strong base. If this were a strong acid in the beaker underneath the burette, what would the pH of the equivalence point be if it was strong? 7. A strong titration is always 7 at the equivalence point because everything in the container is neutral. This equivalence point is not 7, it's 8, which actually tells us that we have a weak acid in this container. So to start, point Q. Point Q will look like this. Technically a little bit dissociates, but if I break up one of those, that's a 25% dissociation. That's not going to happen. So here we have all weak acid. Point Q, we have all weak acid. Then we start adding NaOH. So point R, I've added 1 NaOH into the beaker. Now, as soon as this NaOH gets added into the beaker, a neutralization reaction will occur. Neutralization is when the acid reacts with the base to form a salt. So in that case, it'd be Na plus and A- and water. So here's actually what we would have at point R. So notice how Na plus and A minus are separated, and the reason that they're separated is because in the neutralization reaction we would technically form NaA. A minus is any anion. Could be F. But because it combines with Na plus, remember any ionic substance that has Na in it dissociates. It's a strong electrolyte, so that's why it stays broken up. Point S. I'm going to add another NaOH. So again, I have another NaOH in here. The acid will neutralize the OH minus. Now point S, we've hit a special point on the titration curve because we have equal amounts of weak acid and conjugate base. Weak acid and conjugate base in equal amounts is the half equivalence point. So point S is the half equivalence point. Point T, so now we add yet another NaOH. I have space for my NaOHs. Add another NaOH. Another acid molecule will neutralize. And now notice how we have more A minus. So I'm going to move these water molecules just to save us some space as we're looking. Just think, there's water in here. We know there's water in here because it's in solution. So here's really what we have in the beaker. So we still have a buffer. As soon as one drop of NaOH is added, up until we hit the equivalence point, we have a buffer. Because we have a weak acid and its conjugate base. And then finally, point U. So notice how we skip the equivalence point. I'm going to represent the equivalence point. We're just not going to draw the particle diagram. So if I add one more NaOH in here, another OH minus, there's still an acid that can neutralize OH minus and form water. So now we have another water molecule. This represents the equivalence point. This represents the pH of 8 right here. So after we had 40 milliliters of NaOH, 40 milliliters of NaOH, we hit the equivalence point. The pH is 8 because A minus here is a weak base. So the pH of the equivalence point is basic. Now, if I add one more OH minus, or I guess one more NaOH. So I put another NaOH down in here. There is no more acid to neutralize that OH minus. This represents point U. This represents point U. Because at this point, we've passed the equivalence point. Na plus, though, doesn't affect the pH. It's just a spectator ion. What affects the pH in here is the A minus and the OH minus. So this is showing what's happening along this titration curve. The two most important points, half equivalence point and the equivalence point. Half equivalence point is important because you have equal amounts of the weak acid and the conjugate base. So pH equals pKa. And then the equivalence point is important because that's when all of the acid has been neutralized. So all the acid has been neutralized by the base, so in this case by NaOH. So for example 11, it says a 30 milliliter sample of a 0.05 molar solution of hydrogen carbonate, HCO3 minus, was titrated with 0.05 molar hydrochloric acid. Sketch the expected titration curve given the following information. Okay, so they want us to actually show the curve. So I'm going to go ahead and kind of get a general curve started. On the y-axis is pH, and on the x-axis is volume added. Now here's what I want us to think about because we can be more specific with that x-axis. So we have a beaker. We have a burette. So we have one substance in here, we have another substance in here. When it says it was titrated with HCl, that means that HCl was in the burette and was dripping down into the beaker. Which means in the beaker, we're starting with HCO3 minus. So volume added, this is going to actually be of HCl on the x-axis. Now let's think about this. Every titration is an acid reacting with a base. So here's my strong acid, which means that HCO3 minus has to be a base because titration has to be an acid plus a base. Is HCO3 minus a strong base? No, right? It doesn't have hydroxide and it's not part of that lowercase b on the periodic table. So this is a weak base. Notice that they gave us the starting pH. So they tell us that before any HCl was added, the pH was 9.53. Then they tell us the pH at the equivalence point. Right, the pH at the equivalence point, which is somewhere out here, was 3.83. And they also gave us the pKb. Now, before we can do anything else, we actually need to calculate something. We need to know how much HCl was added at the equivalence point. I need to know when I put my pH of 3.83, what volume was added. So that's the one calculation that we're going to do. So since we don't know the volume, I'm going to say solve for volume of HCl at equivalence point. Equivalence point. If you are trying to find the molarity or the volume at the equivalence point, it is nothing more than stoichiometry. We have volume, molarity. We have molarity of HCl. I'm going to show you a little trick here. Because what do you notice about their molarities? They're equal. Something else that we know is true at the equivalence point is that moles are equal. Right? Moles of acid equals moles of base. Not bases, just base. So if moles are equal at the equivalence point, and molarity is equal at the equivalence point, volume is also equal at the equivalence point. Volume of HCl added at the equivalence point is 30 milliliters. Now, could you do a stoichiometry problem? Yes. Here's what I could do. I could say, I know I have 0.05 molar HCO3 minus, X moles, 0.03 liters, and I can solve for moles of hydrogen carbonate. And then I know that these moles are equal at the equivalence point. Because that's the definition of an equivalence point, is that moles are equal. Moles of acid equals moles of base at the equivalence point because it's completely neutralized. And then I could use moles and molarity of HCl to find volume. I could do the same thing over here. And I could solve for liters. I find that it takes 0.03 liters of HCl to reach the equivalence point. So that's important because I can do this. I can say that this is 30 milliliters. And you might say, well, why is that important? Well, if it was a free response question, they give points based on different parts of the titration curve. One of the points that they would give would be to have the pH at the equivalence point at 30 milliliters. Say this is 3.83. Now we have one more. We have one more point that we can actually put on here. Because this is a weak base, strong acid titration. We can actually figure out the pH at the half equivalence point. Now, this is the pKb, something that's important to remember. If this is a B, this should be OH. At the half equivalence point of a weak base titration, pKb equals POH. Well, if this is POH, how do I figure out pH at the half equivalence point? Subtract it from 14. So the half equivalence point is 6.37. Now the half equivalence point happens at half the volume. So at 15 milliliters, the pH is 6.37. Again, at 6.37 because pKb equals POH at the half equivalence point. Subtract from 14 to get pH. Now when you're drawing a titration curve, some tips that other teachers that actually grade the AP test have given is just as you're drawing the curve to help you remember, since this is the half equivalence point, put a horizontal line through that dot, through that point. For the equivalence point, put a vertical line through that. Because that reminds you when you're drawing the curve to kind of flatten through the half equivalence point and go straight down through the equivalence point. Because right away when people see these 3 points, they're like, oh, it's a straight line. But titration curves have that S shape. So I'm going to start up here. Because this is a weak base, strong acid titration, we're going to have a little bit of a curve to start. We're going to come down through the half equivalence point, straight down through the equivalence point. And because this is HCl, I would say maybe ending at a pH of 1 or 2. All right, ending at a relatively low pH. You're not going to go all the way down to 0, but ending at a relatively low pH. All right, and so again, this just kind of comes down. Maybe it doesn't come down as much as I drew it, but something like this. Whether you draw it with this curve or kind of more straight down, essentially you want it to go more horizontal through the half equivalence point, straight down through the equivalence point. And this is a weak base, strong acid titration. We don't see it as much, but it's important that you can look at both of them. Next week, we're going to focus a lot more on the weak acid titrations. So this is looking at drawing the titration curve. Looking at actually drawing the titration curve. So just thinking about all of these different points that are important on a titration curve. Questions on this? So example 12, we're actually going to not calculate, we're just going to estimate. So for example 12, I know it says calculate the pH. We're going to just estimate this pH. So there are two parts. There's a part A and a part B. So if instead of calculate right here, you want to write estimate, oh, it's in my eyes. You can write estimate the pH at the equivalence point. So we're thinking about what type of titrations that we're working with here, because depending on what is in the container will change the pH at the equivalence point. So again, here we're just going to estimate the pH. So in part A, NaOH with HBr. All right, it says we're titrating these solutions with HBr. What is HBr? Strong acid. So in part A, we have a strong acid, which is HBr, titrating NaOH. How would we classify NaOH? Is it a strong base or a weak base? Strong base. So if we have a strong acid and a strong base, your titration curve, for titrating these, so we're starting with NaOH, ending HCl. It's almost going to look like this, because titrating NaOH with HBr means that HBr is in the burette and NaOH is in the container. Now, because this is a strong acid, strong base titration, what is the pH at the equivalence point of any strong titration? 7. So our answer for part A is 7. The reason that it's 7 is because if you look at this neutralization reaction, acid plus base yields salt plus water. The salt is NaBr. Na plus is neutral because it comes from a strong base. Br minus is neutral because it comes from a strong acid. H2O is neutral. Everything is neutral. So B, we have NH2OH. So it's got this OH, which means it's a base. But is NH2 one of the cations that would produce a strong base? No, this is a weak base. And we're adding HBr, which we already said is a strong acid. So now if I think about this titration curve, I'm going to start at a little bit lower of a pH. I don't know, maybe 9 to 10. Come down. Oh, not like that. Need a little buffer curve. It's fine. Okay, good enough. This is really what I'm focused on. So here's our starting weak base. We're ending at a relatively low pH because it's a strong acid that's being added. Where would we expect the pH to fall? Above 7, at 7, or below 7? Below 7. So this, the actual number, not as concerned about, but it will be below 7. Here's why. We look at the neutralization reaction here. Neutralization is just a double replacement reaction. So we have H2O, which is neutral because water is neutral. So H and OH combine, which leaves us with NH2Br. Here's our salt. Now we know that Br minus is neutral because it comes from a strong acid, which means that NH2 plus comes from a weak base, is a weak acid. So in this neutralization reaction, the salt is actually acidic. And so since the salt is acidic, it's going to cause the pH at the equivalence point to be below 7. The salt is what determines the pH at the equivalence point of any titration. The salt is what determines the pH at the equivalence point of any titration. So in the case of part A, NaBr was neutral. And H2O is neutral. That's why the pH is 7. Okay, so let's look at, oh, there it is. Okay. So for example 13, so this is actually a pre-response question, right, or part of a pre-response question. So if you read through this, it says answer the following questions regarding a 0.05 liter solution of a 0.1 molar weak acid. So we have the concentration and the volume of a weak acid. They also gave us the Ka value. So on a test or a quiz, I told you that they will always give you the Ka value. They'll give you the values that you need. The solution is titrated with 0.1 molar NaOH. The pH at the equivalence point is approximately 10.2. So they gave us a lot of information here. And what I want to do off to the side is I want to think about what we know. So in this, we know that we have HY being titrated with NaOH. Titrated means it's going through a neutralization reaction. So that means that I'm creating H2O and NaY. Y is some anion, could be anything. This just lets me think about what's actually happening in this container. So they tell us that we have 0.05 liters of a 0.1 molar solution of HY and 0.1 molar solution of NaOH. Whenever it's asking about volume or molarity at the equivalence point, that is a stoichiometry problem. Now, could you look at this and do it without stoich? Yes. You can recognize that you don't need stoich, that's fine. I'm going to go through the stoichiometry though. At the equivalence point is important because this is where moles of acid equals moles of base. This is where all of the acid has been neutralized by the base. So think about what you have. This is why writing down our information is useful. I have molarity and volume of HY. I can figure out how many moles of HY we had at the equivalence point. So I'm going to say we have 0.1 molar, which is X moles of HY over 0.05 liters of HY. So I can solve for X. .005 moles of HY. We know the equivalence point, these are equal. The reason these are equal is because it's a 1-to-1 mole ratio. So this equals 0.005 moles of NaOH. They are equal because we are at the equivalence point. The definition of the equivalence point is when the moles of acid equals the moles of base. It's completely neutralized. Well, now if I have the moles and the molarity of NaOH, I can figure out the volume. Because the point of this question was to find the volume. And it just says volume, so we can solve in liters and that can be our answer. So multiply X over, divide by 0.1, get 0.050 liters of NaOH. Notice that's the same volume of HY that we had. That's why I said if you could do it without stoic, you recognize that the molarities are the same. At the equivalence point, we know that moles are the same. Molarity is moles over liters. If molarity is the same and moles are the same, liters also have to be the same. So that was part A, calculating the volume of base at the equivalence point. Part B, calculate the pKa for the weak acid. Now, I'm not going to lie to you. When I looked at this at first, I was like, I don't have the titration curve. How am I supposed to find the pKa? And then I looked back and said, oh, well, they gave us the Ka. They gave us the Ka right here. What does this lowercase p mean? What do you have to do? Take the negative log of Ka. Take the negative log of 1.8 times 10 to the negative 8. From the estimation, we know it should be somewhere around 8. When you actually plug it in your calculator, the pKa, 7.745. pKa, 7.745. And then part C, determine the pH of the original acid solution. This is going back and reviewing weak acids. pH of the original acid solution. You're finding the pH of a weak acid. The original acid solution is a weak acid. If you're like, well, I know it's weak, I'm just going to write the equilibrium. HY is at equilibrium with H plus and Y minus. We know that. It's a weak acid. So this is before. Original acid means before any NaOH is added. To find the pH of a weak acid, we did this in chapter 16. You put it at equilibrium with its ions. If you need a calculation, you use an ICE table. Then you go through and you solve. The original acid solution, the only thing that we have is HY. The only thing we have initially is 0.1 molar HY, and then we fill in our ICE table. So 0.1 minus X, X, and X. This is an acid because it produces H plus. So since it's an acid, we use the Ka expression, and they already gave us Ka. So 1.8 times 10 to the negative 8. Going to assume X is small. That allows me to ignore this minus X on the bottom. So we can solve like we did. For X. For X, I got 4.24 times 10 to the negative 5th. Look back at your ICE table and see, what does X represent? See that X is actually H plus. That's important because now that I have H plus, how do I find pH? Take the negative log of that. Once I take the negative log, pH is 4.372. In example 13, we went through A, B, and C. The last part of this is sketch a titration curve. So part D says sketch a titration curve for this experiment. When you sketch a titration curve, The y-axis is always pH, and the x-axis is always volume of what is being added. So because it says the solution is titrated with NaOH, that means that NaOH was in the beaker, or in the burette, being added to the weak acid in the beaker. So we're going to label this volume of NaOH added. Now, some things we want to think about when we are sketching a titration curve. We want to think about the starting pH. I'll kind of write this off to the side and then we'll fill it in. The starting pH is before any NaOH was added. So when volume of NaOH added is 0, we can think about our starting pH. Our starting pH was the initial pH of the acid. So for this experiment, I'm going to put it here. It was 4.372. That was our starting pH before any NaOH is added. Then, if we can, we want to figure out the pH at the half equivalence point. Now, I like doing the pH at the half equivalence point after I've done the equivalence point, and I'll show you why. So the next thing I want to think about is pH at the equivalence point. We figured out the pH, well, we figured out the volume needed to go to the equivalence point. Now, I'm going to treat this as milliliters just because it's going to be an easier scale to use. So 0.05 liters is 50 milliliters. So here, I'll go ahead and put 50 milliliters. That was the volume needed to reach the equivalence point. And in the prompt, they told us the pH at the equivalence point was 10.2. So I'll go ahead and just put a dot up here. It's 10.2. Is this to scale? No, we'll just do our best. Now remember, at the equivalence point, to help us draw, it'll help to put a vertical line through the equivalence point dot. Now the half equivalence point, the reason I like to do it after the equivalence point is because remember the half equivalence point is half the volume. So if the volume at the equivalence point was 50, the volume at the half equivalence point would be at 25 milliliters. Now the pH at the half equivalence point is equal to pKa. So over here, I'll label, right, the pKa is the pH at the half equivalence point. So here maybe 7.745. I'm going to put a horizontal line. Put a horizontal line through the half equivalence point. So here's the equivalence point, where moles of acid equals moles of base. The half equivalence point is where pH equals pKa. And so that's pretty much it. We didn't look at final pH, but we know because it's NaOH, it's going to be relatively high. So I'm going to start by kind of drawing this buffer region. So I'm going to start with something like this. Now, if my scale was correct, it might look a little bit better. But notice up here, I ended maybe at a pH of 13 to 14 because it was NaOH. So here's our titration curve. Mine isn't as smooth as the ones that you saw in the video. You can see the smooth ones in the video, kind of what they're supposed to look like. But you have this buffer region, and then you have your equivalence point. That's close. So that was part D. Questions on this one? So we're going to look at example 14. You can tell from this that example 14 was also a free response question. I'm trying to show you more of the free response questions rather than like textbook questions, because these are the types of questions you're going to see more. So with this, it says diethylamine. There's that amine, A-M-I-N-E, the weak base that reacts with water to form a basic solution. So this is the prompt. They're giving you everything, right? This reaction. Part A, write the equilibrium constant expression for this reaction. I know you know how to do this. Equilibrium constant expression. That's K. You do part A. Write the K expression. Think about what dimethylamine is, what it produces in the reaction, to figure out if it's Ka or Kb. You have to be able to recognize whether it's Ka or Kb. Think about what gets included, what doesn't get included. So here's the reaction that they gave us. If I write the K expression, it's products over reactants. So it's the concentration of this conjugate acid times OH minus over just dimethylamine. No water. Right, technically, this says aqueous. College Board missed that one. All right, water's a liquid. So we're not going to include water at all. Now, it says that diethylamine is a weak base, which means this is the Kb expression. Plus it produces OH minus. If you see OH minus in the K expression, it's Kb. You see H plus or H3O plus, it's Ka. So part B says the pH of a 40 milliliter sample of a 0.850 molar diethylamine solution is 12.522. There's the pH. Part 1, calculate the molarity of hydroxide. So I'm going to figure out what's the molarity of OH minus. I know that we've gone through a lot of different calculations, but if you have to, use your equation sheet. All right, use your equation sheet. If you know pH, what else do you know? Or what can you find? POH, then you can go to OH minus. Or you can go H plus and use KW to go to OH minus. I would recommend doing POH. So 14 equals 12.522 plus POH. This is one way you can solve. And so POH, if you subtract is 1.478. If you know POH, you know OH minus, because remember that the concentration of OH minus is 10 to the negative POH. Just like H plus concentration is 10 to the negative pH. This is actually a very good scaffolded question, very common free response type of question. You kind of start from the basics and then you're working up. So 10 to the negative 1.478. I got 3.32 times 10 to the negative second molar. Or 0.0332 molar. Now that's OH minus. And more specifically, that's OH minus at equilibrium. That's OH minus at equilibrium. The reason that's important is because for part 2, calculate Kb for diethylamine. Now you could set up an ice table, or some people will look and they'll say, well, I know what OH minus is at equilibrium, so I know what the other product is at equilibrium. And I know that diethylamine is the initial minus equilibrium amount. So if you wanted to set up an ice table right underneath here, you could. And so we know that this is 0.850. We don't start with anything initial here, but we know equilibrium for OH minus is 0.0332. So we know the change. We know the change. So then I actually got 0.8168 for the equilibrium amount of diethylamine. And then we can plug into our Kb expression. 0.0332 squared on the top over 0.8168 on the bottom. Because again, Kb is equilibrium. So for diethylamine, we had initial minus the equilibrium amount. Because that's not enough to completely ignore and just put in 0.85. And so I got a Kb value, 1.35 times 10 to the negative third. For part 3, start by determining the pKb for part 3. So for part 3, it says determine the pH at the half equivalence point. We don't even care about the rest of this. We don't care about 40 milliliters is titrated with HCl. The importance here is pH at the half equivalence point. Now we know that pH equals pKa at the half equivalence point. However, we don't have a pKa here. We just solved for Kb. So if we're working with a weak base, we also know that POH equals pKb. So if you found the pKb, take the negative log of this. Negative log 1.35 times 10 to the negative third. Let's see. Log. The pKb is 2.87. Now again, pKb equals POH. B is for base, OH is for base. Subtract from 14. The pH at the half equivalence point is 11.13. And then part 4. I'm going to do part 5 on a different slide. Part 4, determine the volume of HCl required to reach the equivalence point. Volume is stoic. Determining volume or molarity at equivalence point is nothing more than stoichiometry. So I have 40 milliliters and 0.850 molar diethylamine. Remember, at the equivalence point, our moles are equal. Moles of acid equals moles of base. going to say 0.850 molar, X moles over 0.04 liters. Right now I'm solving for moles of diethylamine. Right now I'm solving for moles of diethylamine. We know that it's a 1-to-1 ratio. If we wrote out this equation, we would find that it's a 1-to-1 ratio, which is why this is also equal to moles of HCl. It's also equal to moles of HCl. Now we know the concentration of HCl. We know the moles of HCl. We can find the volume. It just says volume, doesn't specify what unit. So multiply X over and divide by 0.7. 0.0486 liters, which is 48.6 milliliters. So parts 1 and 2. So I guess part A and then B1 and 2 we looked at in chapter 16. Part 3 and 4 we were looking at titrations. Now part 5. This is where the work really happens with titrations, and it's like part 5. Determine the pH at the equivalence point. So pH at the equivalence point is not just stoichiometry unless it's a strong acid, strong base titration. If the 40 milliliter sample is titrated with 0.7 molar HCl. So this is actually where we're going to go back, and this is why we did the neutralization discussion last Friday. Because this is where we have to think about adding volume to volume. So taking into account the dilutions, taking into account the stoichiometry, and taking into account equilibrium. So this is where we kind of have 3 different steps. So we have, this is when we have the pH at the equivalence point. We have 3 steps. That's still lit. We have dilutions. So we have dilution that we have to take into account. Adding volume to volume, you change the molarity. Then we take into account the stoich. Then we take into account the equilibrium. So dilution, stoich, and equilibrium. So if we start with part 5, let's start by taking into account the dilution. Because what we're doing is, let's do this. We have diethylamine, C2H5NH, and HCl. We're adding volume to volume. We're adding 40 milliliters to 48.6 milliliters. This is what we just found. We're adding those volumes together. That's going to change the molarity. So I'm going to figure out what's the new molarity of diethylamine, what's the new molarity of HCl. And we can use molarity as our stoichiometry. So let's do M1V1 equals M2V2. Remember, that's dilution. So diethylamine was 0.850 molar. We had 40 milliliters of it. I'm going to find the new molarity when these get added together. So the new volume is 88.6 milliliters. So the new molarity of diethylamine is 0.384 molar. Notice I'm almost cutting it in half, a little more than in half. When you add two solutions together, you're adding volume to volume. You are changing the concentration. By doing this dilution, we're actually saving steps by having to go to moles, then do the stoic, then go back to molarity. We're actually saving some time. So I'm going to do the same thing for HCl. So HCl, we have 0.7 molar. We had 48.6 milliliters of that HCl. I'm going to find the new molarity when I add these two solutions together. So before they react, I'm finding what their new molarity is. So both of them have a new molarity of 0.384 molar. Diethylamine becomes 0.384 molar because of the dilution. Hydrochloric acid becomes 0.384 molar because of the dilution. So now we took into account adding volume to volume. Then we look at the stoichiometry. Stoichiometry is a single arrow. This is neutralization. So if we actually look at what this becomes, HCl is the acid. It's going to donate its proton. We're actually going to get D2H52. H is going to donate its proton, so it's going to become NH2+. We'll have Cl-, and that's it. Now, if I wanted net ionic, I could actually ignore the Cl's. I'm actually going to ignore the Cl on this side because this is neutral. Cl- is not going to affect the equivalence point. So here's actually what happens at the equivalence point. Do this just to kind of separate it. A titration is nothing more than a neutralization reaction. So a titration is nothing more than a neutralization reaction. At the equivalence point, the base and the acid are completely neutralized. They're gone. And so all we have is the salt and water. Within the salt, we look at what affects the pH. Since this is a weak base, diethylamine is a weak base. This is a weak acid. It's its conjugate acid. That is what affects the pH. Now we have to figure out how much we have. So I'm going to write it down here at the very bottom. I'm going to think about stoichiometry in a very general way. I have 0.384 molar diethylamine, 0.384 molar HCl. Do I have a limiting reactant? Does one run out first? No. We would call these co-limiting. We use them all up completely. So here I'm just showing the stoich. These are being used up completely. As these are being used up, we are forming products. 0.384. Technically, we're forming 0.384 molar Cl- as well. I'm ignoring Cl- because it's neutral. It's not going to affect the pH. It doesn't matter how much of that you have. So after this stoichiometry, after this neutralization reaction, we have no acid and no base left over. They're gone. Instead, what we have is the conjugate acid in the container. So the stoichiometry took that into account. The last thing we have to do with equivalence point is focus on the equilibrium. The reason we have to focus on equilibrium is because this is a weak acid. So if we look at what this is like in the container, this is a weak acid. We know it's a weak acid because it's the conjugate acid. So if we have just this weak acid in the container, and you can include water if you want, we have C2H52, NH2 plus. This is an acid, so if you want to represent it with water, you can show water being the base. This is a weak acid. It exists at equilibrium. So this is the acid, it's donating one of its protons to become C2H5NH. Base will accept the proton to become H3O+. This is what is in the container. So now it becomes an ice table. When you add volume to volume, when you are finding the pH at the equivalence point of any weak, strong titration, you go through these steps. Take into account the new molarity, so for dilution, then the stoichiometry, how much product are you making, then equilibrium, because you're going to have something weak in the container, and that is what affects the pH. So now here, water doesn't matter because it's a liquid. The only thing we had in the container after this neutralization reaction was this weak acid. We had 0.384 molar. We had nothing else. Now this looks like an ice table that we've seen. So we have minus x, plus x, plus x. Now, if this produces H3O plus over here, what K would we need? Ka. If this produces H3O plus or H plus, that means it's an acid, we would need Ka. Well, if I look back at the problem, we were not given Ka. However, we did calculate Kb for the base. Remember that Ka times Kb equals Kw. We're trying to find Ka for this conjugate acid. The Kb that we calculated was 1.35 times 10 to the negative third, and Kw is 1 times 10 to the negative 14. And so we can actually get a Ka value if I divide this over of 7.41 times 10 to the negative 12. There's our Ka. Determining the pH at the equivalence point takes lots of steps because we have to take into account dilution, then stoichiometry to figure out how much salt we're making, then look at equilibrium. But when we're looking at the equilibrium, we're looking at a conjugate. So we have to use the idea that Ka times Kb equals Kw. And now finally, we can plug this in to the Ka expression. 7.41 times 10 to the negative 12 is x squared over 0.384 minus x. I'm going to assume x is small. That allows me to neglect that minus x. So multiply over, take the square root. I got 1.67 times 10 to the negative 6. That was x. If I go back and I actually look at what I'm trying to find, I'm trying to find pH at the equivalence point. pH at the equivalence point means I'm trying to find x, which is H plus. And now finally I can take the negative log of that. Take the negative log of H plus 5.773. All of that for part 5, just to find the pH is 5.773. Now you can see why there are some questions that take a while. The questions that take the longest are determining the pH at the equivalence point. If it's a strong titration, well, the pH at the equivalence point is 7. You don't have to do a calculation. But when you have a strong, weak titration, you have to go through dilution, then stoichiometry, then equilibrium. Now we're just going to do example 16, which is a nice short and sweet question. We'll save 17 for Monday. So before I flip to 16, any questions on what we did in 14? So example 16, use the following table to determine which of the following would be the best indicator to use to indicate the equivalence point. So we have two parts here, A and B, which are pH at different values. And then in the problem, they gave us 4 indicators with Ka values. And I'm going to show you how we can do this without a calculator. And we'll actually get correct values because of the Ka values that we were given. So again, in this example, use the following to determine which would be the best indicator. So remember that an indicator lets us see pH changes qualitatively. So these change colors when they are in a certain pH range. So within that range, they'll change colors. Now, the first thing that I would recommend doing is finding the pKa. Because the pKa will help us determine the pH range of this indicator. Because these are 1s in front of the scientific notations, when you take the negative log, your answer is actually the absolute value of the exponent. If you don't believe me, you can put it in your calculator. If you do negative log of 1 times 10 to the negative 4, your answer is 4. 5, 7, and 9. Now the importance of pKa is that the pH range is pKa plus or minus 1. So here I'm going to add pH range, and that is pKa plus or minus 1. What you need to know about indicators is what range would they change. If you have Ka or pKa, what's the range? Well, if this is a pKa of 4, the range is 3 to 5. Methyl red is 4 to 6. Bromoethyl blue is 6 to 8. Phenolphthalein is 8 to 10. So these are the ranges. These are the ranges that the indicators change color. So for part A, if you want the pH at the equivalence point of 7, you want to pick the indicator that has a range where that pH falls. So for part A, it would be bromoethyl blue. Because bromothymol blue's pH range is 6 to 8, so 7 falls right in there. And then pH at the equivalence point of 3.52, you would say methyl yellow. That's what you need to know about indicators. That's it. Nice, easy example to end on.